Hey all your sense, this is Pradesh Chaudhary Quantum Group. Let's see this very good question of physics from electrodynamics. It's a question of motion of charged particle in EM field. So here's this question. The question states there is a uniform magnetic field B is equal to B minus K cap. So this is XY plane and the magnetic field is uniform in along the negative Z direction. So according to our usual way of speaking, that is going into the plane of the page. And there is this charged particle initially at origin at t is equal to 0. It is at origin, charge is minus q, mass is m, and it is projected with velocity v naught along the y direction initially at t is equal to 0. So in addition to the force that the magnetic field will act, there is a damping force. The damping force always act towards the opposite to the velocity, and the damping force is a kind of a dissipative force. Resistive force always dissipative force, so the particle will keep on losing its mechanical energy. So we have to consider two forces. One would be obviously the magnetic force q v cross b, and there is this minus kv. K is the damping constant, that is a constant. So we have to discuss the trajectory of the particle, speed of the particle as a function of time, the coordinates of the point where the particle finally stops, total distance traveled by the particle before it stops, and of course we will also find the speed of the particle as a function of the distance traveled. So these are the things we want to discuss. So when I say trajectory, that will discuss qualitatively. We are not going to derive the expression for the equation of trajectory. So suppose if this force was not there, the damping force was not there, so this is v naught, so there would be a magnetic force at t is equal to 0, q v cross b, so this is v and b is into, so v cross b in this direction. Because of the mirror effect, my orientation would be coming to be opposite, so just make a necessary adjustment. So v cross b would be along this direction, and there is a charge negative, so v cross b will be q v cross b will be in this direction. The center would be here, so it will move in the circle, something like this. It will move in a circular path. But then there is this force. The nature of this force is to dissipate mechanical energy continuously. It will decrease the speed. This is always opposite to the tangential direction, so it will continuously decrease the speed. Magnetic force, the job of the magnetic force is only to change direction. It cannot change speed. So speed will continuously decrease. So it will rotate. Magnetic field, magnetic force is there that will rotate, but at the same time its speed will decrease. In uniform magnetic field, the radius is equal to the radius in the magnetic field, if the particle is projected perpendicular to magnetic field, the radius is mv by qb. So mv is equal to p divided by qb. So p is equal to qrb, that is a momentum. And as the particle is moving, because of this force, it is losing continuously kinetic energy, so momentum will also be lost. So its momentum is lost, so its radius will continuously decrease. So the path would be something like this. It will be something like this. It will go like this, go like this, go like this. Speed is decreasing, and the radius is decreasing, and like this, like this, like this, like this. It intuitively it looks like you might have done a question the kinematics. So it may take infinite time to eventually come to a stop, but that point would be a finite point, so it will stop at a certain point. So first we will find the coordinate of the point where the particle finally stops. So let's go to the next page. So that is this thing. So first let me write the boundary conditions. What are the boundary conditions at t is equal to 0? So at t is equal to 0, the xy coordinates are 0 because particle is at the origin, and the velocity x component of the velocity is 0 and the y component of the velocity is v naught because particle is projected along the y direction. Now it moves in a spiral path, something like that, and eventually it stops. So finally, let's assume that it stops at a point whose coordinates are x naught, y naught. So x is equal to x naught, y is equal to y naught. It's finally stops, so both component of the velocity x and y will be 0. And let's note one thing also. Initial velocity in the y direction, magnetic field is in the negative z direction, so magnetic force is qv cross b, so that will be perpendicular to b vector, so magnetic force will always be in the xy plane, and damping force will be opposite to the velocity, so the particle will always be in the xy plane. So at a general moment, we can write the velocity vector of the particle is some vx I cap plus vy j cap. So that is the trajectory, and this is the point where it stops. So we assume that the coordinates of this point are x naught, y naught, and this is a general point x comma y. Here the component velocity is always tangential. I have assumed that the x component of the velocity is vx and y component is vy. So like this is the velocity, and the opposite to velocity, the damping force will be there, and if v is there, b is there, so v cross b will be in this direction, and charge is negative, so magnetic force will be perpendicular to velocity, like that, and that is the force. The job of this force, magnetic force qvb, is to rotate, and the job of this force kv is to decrease the speed. So we want to apply the Newton's first law at a general moment here. So ma is equal to f net, and in f net, ma we can write because the particle is moving the xy plane, so I am writing a vector as a axi cap plus ayj cap. F net is the vector sum of these two forces. This is a minus kv vector. Minus kv vector means minus k vx I cap plus vy j cap. So that is this force in the vector form, and this is actually charge is minus q, velocity vx I cap plus vy j cap, and then cross b vector. So applying qv cross b, so I am writing here the magnetic force. So this is a charge is minus q, vx I cap plus vy j cap k cap j cap cross the magnetic field b minus k cap. So for this term, make a cross product. So I have written this here, so that will be vx, this minus q into minus b will become first of all qb, and I cross k cap is equal to I cap cross k cap is minus j cap. So this term will be qb vx minus j cap, and j cap cross k cap is I cap. So this term will be qb vy I cap. So club the I cap term. So clubbing the I cap term here, minus vx plus qb vy I cap, and the j cap term is minus k vy and minus qb vx j cap. So compare from here I cap term and j cap term from both sides. So we can write max is equal to minus k vx plus qb vy, and also may is equal to minus k vy minus qb vx. So the main job is done, and now using the boundary condition we can arrive to the coordinates where the particle will finally arrive. So let's go to the next page. So this is what I just stated, max equal to minus k vx plus qb vy, and may is equal to minus k vy minus qb vx. So that is the summary that we obtained. This is the boundary condition, and finally that is the final boundary condition. This is the initial boundary condition, and f is equal to ma, that was. Now using this, just want to rewrite this equation. max is equal to minus k vx plus qb vy. So ax can be written as dvx by dt. That is the x component of acceleration. There is a rate of change of x component of velocity. So Ax is equal to dVx by dt. Same way, Vx is the x component of velocity, that is the rate of change of x coordinate. So this is dx by dt. Similarly, Vy is equal to dy by dt. So rewriting this equation, I am writing m into dvx by dt is equal to minus k into dx by dt plus qb, actually this is plus here, so plus qb dx by dt. So you just multiply both side by dt, so we will get mvx is equal to minus k dv dy plus qb dx, like this. And now integrate this equation both sides. So integrate, and now put the limit using the boundary condition. At the lower limit the initial boundary condition, at the upper limit the final boundary condition. So initial Vx is 0, initial Vx is 0 here, initial x is 0 here, initial y is 0 here, and final Vx is also 0, final x is x naught, and final y is y naught. So just putting these boundary conditions, so this integration would be 0, and that would be minus kx naught, and that would be qb y naught. So that is my first equation. From here I can simplify for y naught. So y naught would be k by qb into x naught. So that is the thing I will use. And now this thing, may minus kvy minus qbvx, again just in place of ay write dvy by dt, in place of vy write dy by dt, in place of vx write dx by dt. Same way multiply both side by dt, so that will become, this equation will become m dvy is equal to minus k dy minus qb dx. Integrate both sides, put the lower limit, upper limit, lower limit for the initial boundary condition and upper limit for the final boundary condition. Initially Vy is V naught, y is 0, x is 0. Finally particle rest, so final Vy is 0, final y is y naught, final x is x naught. So now integrate it. So this integration would be m into minus V naught, that would be minus ky naught, that would be minus qb x naught. So just make all positive, so that would be mv naught is equal to ky naught plus qb x naught, and we can put the value of y naught from here to this equation. So mv naught, I am putting y naught as a kx naught by qb, so if I put it here, that will become k square x naught by qb plus qb x naught. So we can take x naught common, so that would be k square plus q square d square by qb x naught. So finally we solved the x coordinate equal to qb v naught qb m, there would be v naught also not written here, so it would be qb m v naught divided by k square plus q square b square, this is the x coordinate finally. And then here just y naught is equal to k by qb x naught, so the x naught here, put the x naught from here, so we will get y naught is equal to km, again there will be v naught here, so km v naught divided by k square plus q square b square. So we got finally the final position where the particle stops. Now we want to find the velocity as a function of time. So let's go to next page. So once again, the particle starts from the origin with initial velocity v naught along the y direction. It will go in the spiral path. So suppose this is t is equal to 0 till time t, particle has come up to here, and here the speed has become v. So V is particle always moves along the velocity, direction of velocity is always along the tangential direction. So this is the tangential direction, and perpendicular to tangential is the normal direction. So this is tangential direction, that is a normal direction. So opposite to tangential direction there is this dissipative force kV, and in this direction there is a qvb. So right now for the calculation of the speed I need not use this qvb. So I am going to write the equation of motion along the tangential direction, and also this is a moment of t is equal to 0, and here that is a moment time t. From 0 to time t the particle has travelled say a distance s. S is the length along the path. So we are applying MAT is equal to FT. AT is the tangential acceleration and FT is the force along the tangential direction. This is tangential direction. The force along tangential direction is minus kV, and AT is always, tangential acceleration always changes the speed, and the normal acceleration changes the velocity. So tangential acceleration is the rate of change of a speed with respect to time. So AT is dv by dt. So AT is dv by dt. So that is m dv by dt is equal to minus kv. So take the v term on one side. So dv by v is equal to minus k by m dt. So integrate it. Initial limit is v is equal to speed is v naught. Time is 0. Final t, and that is v. So if I integrate it, LHS will become ln v by v naught. RHS is minus kt by m. So arrange that, you will get v is equal to v naught e to the power minus kt by m. So that is a exponential decreasing velocity. So like discharging of a capacitor, or the kind of the decay of a radioactive material, it takes infinite time for the speed to decrease, but it will travel a finite distance, it will come to a finite position. So I can also write this thing as a v is equal to v naught t by tau, where tau is m by k. Why I am writing just to get a better feel. So this is a dimensionless thing. So this tau has to be of a dimension of time. And what is tau? Tau I have written in place of m by k. If I make a plot of v versus time, so that is an exponential decreasing graph, something like this. Initial velocity is v naught and it decreases exponentially. One interesting thing is the speed at t is equal to tau. So at t is equal to tau, this velocity will be v naught by e. So this tau is a time at which the speed decreases to 1 by e times, means the 37%. And there is also called mean time. This tau is also called mean time. And now the distance traveled. The same equation MAT is equal to minus kV. This equation, in place of AT we can also write AT as a v dv by ds. So here this equation I am writing in place of AT v dv by ds. Now this v and v will get cancelled. So we will get m dv is equal to minus kds. So integrate this. So with the proper limits, so initially v is equal to v naught, s is equal to 0, and final velocity is, final mean when the distance travelled is s, the speed becomes v. So this is, now integrating this and putting the limit, we will get mv minus v naught minus ks. So v is equal to v naught minus k by m. So that is one interesting thing, is that with time the speed varies exponentially, with s speed varies linearly. So as the speed is decreasing, as s is increasing, v is decreasing. So that is a linear variation. And now we can, using this equation, we can find the total distance travel. This is the distance, as s is the distance when the speed is v. So for the total distance, finally v becomes 0. So if I put v here 0, so we'll get s is equal to v naught m by k. So s is equal to v naught m by k, that is a total distance, and this m by k we can write tau. So s naught total distance is v naught tau. So the interpretation of this mean time is that if the particle would have been moved with the speed v naught, so the total distance would be the same as it would take to move in the time tau, that is the mean time. Similar concept also used in the radioactivity. So overall we have got the expression for the coordinate where it stops. Qualitatively we understood the path would be a decreasing spiral. We can also derive it, that will be a kind of very tedious thing. And we got the velocity as a function of time, we got the velocity as a function of distance traveled, also the total distance. So overall a lot of thing was there in this question. Hope you like this video. If you like this video, please hit the like button and share, and if you don't subscribe, please do subscribe. Thank you.